Hi again. So this is the second part of Chapter 2, and we're going to be talking about valence electrons and the octet rule and how atoms become more stable. So all atoms want to have an outer orbital that is completely filled. If you look here, this is hydrogen. Hydrogen has 1 proton, 1 electron. In the first orbital, you can have up to 2 electrons. So this atom is unhappy, he's unstable, he doesn't have his 2 electrons. Over here, helium has 2 electrons in its outer orbital. Down here we have carbon. Carbon has 2 electrons in the first orbital, can have up to 8 electrons in its second orbital, but only has 4. So carbon is also unhappy. But if we look next door to neon, neon has 2 electrons in its first orbital and then has 8 electrons in its outer orbital. Having 8 electrons in the outer orbital makes neon a very stable gas. Same with helium. Both helium and neon are called noble gases. And all atoms want to gain electrons to become noble gases or to look like a noble gas. They want to have their full outer electron orbital filled. And if they don't, they're going to be unhappy or unstable. So they'll always enter into chemical reactions if they don't have their outer electron filled. So this is known as the octet rule, typically, so excluding like neon or lithium, not neon, I'm sorry, lithium or hydrogen, those really small atoms. Most atoms have an outer orbital that we're going to discuss at least with that has the ability to hold up to 8 electrons, and this is where the octet rule comes into play. The octet rule states that atoms want their outermost orbital or valence shell filled. And having 8 electrons in the outer shell is going to be filled, except for hydrogen, you only need 2. And so they're going to do whatever they can to get the outer electron orbital filled, including losing electrons, gaining electrons, or sharing electrons. And so this is a cab holding 8 electrons. Here's another electron trying to get in. I can't find my mouse. So I can't show you where he is, sorry. There he is, right there, boom, boom, boom. He's trying to catch up to the cab, but the cab is running, and they're basically saying, hey, we're already full, we're happy, we're not going to enter into any chemical reaction with you. So what are the different chemical bonds that can form to make their outer orbital complete? We have ionic bonds, which you see right here. We have polar covalent bonds, which you see here, but I'll talk about a little bit later. Nonpolar covalent bonds and hydrogen bonds. From weakest to most strong, you'd have hydrogen bonds are the weakest, then ionic, then polar covalent, then nonpolar covalent. And so this is a really cute cartoon showing chlorine and sodium. Again, I just got these off of Google Images. I just looked for something that said, oh, cute ionic bonding cartoon. And here's a little chlorine atom saying, I only have 18 electrons. I wish I had one more. And here's sodium saying, hey, I have an electron, you can have it. Are you sure? Yeah, I'm positive. So when they enter into a chemical reaction, sodium gives an electron to chlorine. Electrons are negatively charged. That makes sodium more positively charged, so it becomes a cation. And chlorine becomes an anion, a negatively charged ion, and opposites attract. So here's what's really going on. In the outer orbital of chlorine, there are 7 electrons. Because chlorine can have up to 8 electrons in its outer orbital, it wants 1 more. Sodium only has 1 electron, so it's easier for sodium to just get rid of that 1 electron, and then its outer shell is going to have 8 electrons in it. So sodium donates an atom, or not an atom, an electron to chlorine, forming sodium chloride or table salt. So you have a positively charged sodium ion, a negatively charged chlorine ion, and they stick together because of the attraction principle. With a nonpolar covalent bond, these are very strong bonds, we have equal sharing of electrons. So instead of one atom giving an electron to another atom, they share electrons. And the electrons are going to move around both atoms around each orbital equally. So there are different types of nonpolar covalent bonds. Here's what you saw on the last page, 2 hydrogen atoms sharing equally. Here you have oxygen, and here we have carbon dioxide. All 3 of these are showing nonpolar covalent bonds where the electrons are going to orbit around all of the nucleuses of each of the atoms equally. In this case, we have a single covalent bond. Here we have a double covalent bond. In this, we have a double covalent bond. We could also have, in the case of nitrogen gas, triple covalent bonds. So you can have a lot of covalent bonds. The more covalent bonds within an atom, or not within an atom, within a molecule, the stronger they are, and the harder it would be to tear those 2 atoms apart. Polar covalent bonds have unequal sharing of those same electrons. So in this case, we're looking at hydrogen and chlorine. Chlorine has more protons than hydrogen does, and so the electrons tend to stick closer to the positive chlorine nucleus than the tiny positive hydrogen nucleus. Because of this, chlorine ends up getting a partially negative charge, even though the entire molecule, hydrochloric acid, would have no charge. Hydrogen would get a partial positive charge. And so the best example of this is in water. With water, we end up with an oxygen atom that has a lot of protons, 8 protons, and 2 hydrogen atoms, each that contain only 1 proton. The electrons tend to sit closer to the water or to the oxygen than they do to the hydrogen. So you have this very negative orbital around oxygen and less of an electronegative orbital around each of the hydrogens. This causes the entire molecule to end up with a partial negative charge and partial positive charges. The entire molecule itself has no charge, but oxygen is partially negatively charged, that's what this sign says, and hydrogen are partially positively charged. This makes a polar covalent bond. And that actually leads us to hydrogen bonds. When you have polar covalent bonding molecules, the hydrogens within those molecules can oftentimes be attracted to the partial negative charge of another molecule. And so here we have water. So water is a polar covalently bonded molecule. The hydrogens have less of an electron affinity. So electrons sit close to the oxygens, making the hydrogens partially positively charged and the oxygens partially negatively charged. So the partial positive charge of one hydrogen will be attracted to the partial negative charge of another oxygen. So here we have this hydrogen bond, which is a very weak bond between the hydrogens of one water molecule and the oxygen of another. This can also occur between water and glucose, or water and any other polar molecule. So for atoms to form molecules, or for bonds to be produced, or to break bonds, you have to have energy. Energy, in a nutshell, is the ability to do work and bring about change. There are 2 major states of energy. We have potential energy, which is that stored energy, and I always like to think of it as if you're sitting down watching this and you're eating a snack or eating your lunch or drinking coffee or a soda. The energy in the food or the drink that's sitting in front of you, that is stored energy. But as soon as you take it into your body, you're actually converting it into different energy that can be used as energy of motion. Kinetic energy then is the energy of motion. In our bodies, in the human body, potential energy is stored energy in chemical bonds. So we can change energy from one form to another. And so here's an example. Here is a bicycler trying to bicycle up a very steep hill. This is kinetic energy. He's using a lot of work to get up that hill. He has to use energy to move. So he's not only moving, which is kinetic energy, but he's using energy, serious energy. And so anytime you have to take in energy to do work, that is known as an endergonic reaction. Endergonic reactions are always anabolic reactions. You're building stuff up. So up here at the top of the hill, he's sitting there relaxing, waiting, resting. That's potential energy. So it's stored up energy. He's just waiting to move. And then down here, he starts moving, but now he's releasing energy. He doesn't have to do as much work. He's just like letting the bike do the work for him. So that is an energy out reaction. Exergonic reactions are reactions where energy is released. All exergonic reactions are always catabolic, so you're breaking things down. Remember, anabolic builds things up, catabolic breaks things down. We learned that in Chapter 1. Anytime you are discussing energy, you have to take into consideration the laws of thermodynamics. So these are how we learn about energy transformations. So the two laws that I always want people to know is that first, you cannot create or destroy energy, but you can change it. So we can change energy from chemical energy in the food that we eat to mechanical energy of running. Or we can take food molecules, break them down, and the chemical energy can be used to produce new molecules, new proteins, or fat, or plasma membrane for new cells. The second law of thermodynamics, though, states that whenever we do transform energy, we're going to lose some energy, and that energy is lost as heat. So we always lose energy. So the amount of energy that you gain or that you take in is not the amount of energy that was initially there. You always lose energy. So anything that we eat, we don't gain all the energy from that food. And some of the energy is going to be lost as heat. And the best example of this is, think about when you wake up in the morning and you have to move. So you get up and say it's winter, which it is right now. It's winter, so it's a perfect time to think about this. And it's maybe 65 degrees in your house, so it's chilly, and you get out from under those covers, those nice warm, snuggy covers, and you're cold. And you're like, oh my gosh, it's really, really cold. But at the same time, your bladder is really full, and you have to pee. So you're like, well, okay, grab a sweatshirt or a sweater or a blanket or a house coat, or go pee. Well, I'm going to go pee first. So you run to the bathroom to go pee. After you're done going to the bathroom, you are walking back to grab your sweatshirt, but you see the coffee pot, and you're like, oh my God, I need coffee. Why don't I just quickly get the coffee started so that then when I get my sweater on, I'll be able to function because I'll be able to grab my coffee right away. So you get your coffee ready, and by the time you're done getting coffee ready, you forget that you were cold. You're no longer cold. The reason for this is you're using your muscles. Your muscles are moving, so they're converting energy of ATP into energy of motion, and as we do that, we are losing energy as heat. So when you lose energy as heat, that heat warms up your body, which is why, well, we get warm. So here are some examples of chemical reactions that occur in our body. These are the most common reactions, and these are being shown as words. So instead of reading these as like an amino acid and another amino acid forming a dipeptide of amino acids or a protein, we're looking at just words, okay? So if this is called a synthesis reaction. A synthesis reaction, or an anabolic reaction, you're building stuff up, you're taking two molecules and you're putting them together, forming a bond. So note plus book equals notebook. You need energy. This is an anabolic reaction. It is an endergonic reaction. Here's a decomposition reaction. Bookworm, book plus worm. So this is a two molecules or two words that we put together, and we break them back down into book and worm. That is a decomposition reaction. It is a catabolic reaction, and it is an exergonic reaction. We are releasing energy. Here's an exchange reaction, which has both synthesis and decomposition. So we have notebook plus worm, so all of these molecules. And we end up exchanging. So note, book breaks down into note plus book, but book and worm come together forming bookworm. So we had a catabolic reaction here and then an anabolic reaction here from this and this to form this. So this would be both an anabolic and catabolic reaction occurring in this exchange reaction, which means you're going to release energy, but that energy is going to be used to drive this reaction to build up something else. So what influences chemical reactions? Typically, when you think of anything that's going to increase or decrease rates of chemical reactions, there are three major factors: temperature, concentration, and enzymes. Temperature, this is just kind of a cute picture that I saw. If you have an increase in temperature, it's going to increase the rate of atoms moving. That's what this is depicting. So, you know, in the case of the boy running from the fire, well, he's running from the fire. If there was no fire, he wouldn't be running. So he's moving much faster. It's increasing the rate of the reaction. I always think of this, if you've ever ran in track or cross country, if you were ever in baseball, football, soccer, any type of sport where you had to do some running, before you run, you have to, the coach always tells you to warm up. You have to stretch your muscles, do maybe a lap or two around the field to make sure that your muscles are warmed so that they work better, more effectively. If you are very cold, your muscles don't want to work as effectively. Same thing. Another reaction I talk about is when you take water and you put it on a stove. Water itself all atoms are in motion, but when you put heat under the atoms start moving faster. And so with water molecules start moving so fast that they start rolling, and that's known as a boil. So you can actually see those molecules moving. So that will increase the rate of a reaction. If you have more substrates. So more effective collisions are going to produce more reactions, and so that's what this is showing. You have magnesium and hydrogens over here. The more times they come in contact with each other, the more likely they're going to produce some reaction. And this is just any molecules. If you have more substrates and they're reacting with enzymes, the more the substrates that you have, the more likely they're going to hit those enzymes. If you have less substrates, you're going to have less enzyme, or you're going to produce less products the same amount of time because they're just not going to have as effective of collisions. And then we have enzymes, and so that's what this is showing is an enzyme and stupid mouse. And a substrate. So this is the active site of the enzyme where the substrate binds. Substrate, when it binds, active site conforms around the substrate, gives a little squeeze, and products are produced. So in this case, this is a catabolic reaction because you have one reactant, one substrate, and you have two products at the end. Enzymes decrease the amount of energy it takes for a reaction to occur. And in doing so, they increase the rate of the reaction. So here we have some reactants. And so in this case, we have 2 molecules, 2 reactants. And without an enzyme, the reaction will occur slowly over time, but it'll take a lot longer for the reaction to occur. And in the human body, all reactions are occurring using enzymes. So if there were no enzymes, then the sustaining of life would not be a thing. We need enzymes to increase the rate of a reaction so that we can survive. Just in the pathway of taking glucose and breaking it down to pyruvate, there are 10 different enzymes. Each enzyme is needed to do its job, and that's one pathway in a series of pathways known as aerobic cellular respiration, where we produce ATP. And without ATP, we don't survive. So we need enzymes, because otherwise it would take so long that we wouldn't be able to sustain life as we know it. And so what do? They decrease the amount of energy required for the reaction to occur. So here you need a lot of energy for this same reaction. Here you need much less energy with that enzyme. I'm going to stop here, and then we'll get into water in our next lecture.